So what do you say? Anything you say will be, can be used. Now recording is on. Be careful.
We can cut this part from both days. Don't worry.
Do you know how to do it?
I'm sure, yes, there is a way to
Yeah,
cut it.
very good.
Well, the data is there.
Ah, yeah.
Data is there.
Oh,
Have some cookie, please.
Okay, how's cookie? Chinese cookie.
It's Japanese. We don't finish, I'll bring next week.
That's good. Next week, the building is closed.
Or the week after.
Oh, really?
next week, the
Yeah.
building?
Yeah,
Yeah,
the
there's
week.
there's no power in this building. There will be no power in this building, so.
Good to know.
So come to vacation.
Every work from home. Bucket of like, good and 50 hours from home.
Hello.
That's cool.
Can we have meeting next Thursday?
This is.
This Thursday, yeah. Thursday morning, 11, will that work?
In person?
Yeah, yes. And morning, 11 o'clock, Thursday. Tomorrow is Wednesday.
Oh, okay. Oh,
Will that work, 11 o'clock?
I think so, yeah.
Okay, so shall we just meet here?
Sounds good? Yeah.
okay, sounds good.
Okay, so I suggest we, what?
That's a committee.
Oh. Yes, and I suggest we start at the first welcome to the heat seminar, and next week, Zhao Chen.
Yeah.
Yeah, from
Nice.
Rice University. He will discuss title, very fancy title, probing ultra dense gluonic matter via UPS at the CMS. Why do we need a CMS talk?
I invite you.
Okay, you'll bring the cookie.
Wait, so next week you say this building will be.
The
Yeah,
next will be all be online.
Yeah, it's online.
So
Some cyber cookies.
yes, send the cyber the cookies. That would be nice. So today we're very happy to have Yu Hu from local group. He graduated in 2022 from Fudan University. Then he quit the CME adventure, joined the baryon correlation adventure. Today he will discuss basically the first measurement of d-Lambda correlation in heavy-ion 3 GeV. Please.
Thank you for the invitation. I think it's already
It's been recorded now.
Yeah.
Okay, that's
Thanks for the introduction and good afternoon, everyone. It's my great honor to be presenting this seminar. So I'm a postdoc in the group. Who didn't mention. So today I want to discuss the measurement of p-Lambda, the proton lambda, and deuteron lambda correlation in 3 GeV with GeV collision as star. So let's start. Okay, so I want to start my story from the neutron star. I found a very fancy picture from a Nature cover paper. So neutron star is very high dense object in the universe that we actually know so little about this. But we guess it's probably from the outer crust to the inner core. The density of this star is increasing and become bigger and bigger. Probably in the outer core, it's the state of matter is quantum liquid where the neutron, proton, and electron exist as a soup. They call soup. And then in the most inner core, where we don't know the status of matter, but we guess it's an ultra dense matter. where all the particles break down, and so only quarks, so hyperons. Where to understand the object, one way is to understand the status of matter, where more specifically is phase diagram. So here I found one very beautiful diagram plot where there's two transparent regions shows you the LHC and the RIC experiment. The heavy iron collision is a laboratory to start the dense QCD matter, and this fancy starter, the neutron stars, probably somewhere here. But one way to understand the state of matters is trying to understand the interaction of matters. More fundamentally, it's the interaction between particles, and what called classical way the nuclear potential. So I found a very classical nuclear potential plot here, and just to summarize, if we could understand the nuclear interaction, hypernuclear interaction, this gives us a chance to indicate or to find out probably the inner core status and the outer core of the neutron star. So I found this quite busy slides for just to remind ourselves some history. Many of you may did this experiment when you were college, and many of you may have this question as your first question of your nuclear particle quiz. So
you don't have such a senior people.
okay, so this is a two-particle scattering scattering experiment where we and this is for 1 and 2. I just want to simplify this process. We can write down the pair system wave function as psi, and k here is a momentum of the contains both incident and scattered particles. Where to describe whether these two particles have the interaction, where we have this, we define a parameter called cross section, where cross section T, the total cross section, is equal to the elastic scattering cross section and inelastic scattering cross section. And in this equation, the third L is phase shift. So for this, between these two wave functions. And if we assume a square potential as the most simply situation VR, and we could have the different cases for the wave function UR, and here the A here is a scattering length. So just to quickly summarize this for first part. If we have know the K, the momentum, we know the phase shift, we know the potential, and also know the scattering length. We find in the most simple way, we know how to describe this system. But life is usually not that much simple and easy. So sometimes if we have to deal with like two particle system have different status. For example, people design this experiment. I will not go details to test the cross section for the N proton and neutron cross section, and this for different two spin states. We could still do, but if the system is much more complicated, right? For example, we have hyper, or the particle could be the short time, or if we have not a particle-wise, it's like multi-body problem. How do we do this? That brings to what we want to discuss today, or the heavy iron collision. So I just use RIC and star as an example, and that's actually exactly what I'm going to discuss today. So we use, for example, two nuclear gold collide, and then this. We have after collide, this has the initial information of these two nuclear, and then after collision, this particle will emitting outside, and then after a certain time, we call it time evolution. Like this cartoon shows you, that the particles fly out. So if we studied the angular correlation of those final particles, of course, it contains both the initial information, the emission source, and the evolution of time. This mostly focus on the usually called the flow measurement, right? But if we focus on the momentum correlation of the final state particles, it also contains all of this item, but it can give us, for this, we more or less try to factorize the final state interaction from this system. So that brings to my the topic I want to discuss, the Byron correlation function. As I mentioned just now, we are actually looking at a momentum correlation between two particles, where I call it C, P1, P2, for two particles. This is if we write in the statistical way. If we're approximating the emission process and the momentum of particle, we can write this correlation function into two parts. One in the distribution of the relative distance of the particle pair, SR, and the relative wave function of the particle pair, the psi square, right? So this is including modeling. Well, if we further list the more details of this modeling, there's a very famous, well-used, famous formalism called the Lednicky-Lyuboshitz approach. In this approach, it needs to make the following major assumption. We need a smoothness approximation of the source function. We need use effective range expansion to the psi, and then if we can get the Pyer source radius and all the wave function, where C contains the following items, and there are three. You can find there are three main parameters. That one is Rg, where it corresponding to the Gaussian source of the pairs, if we assume a spherical Gaussian distribution. It also contains the F0 and D0. They are scattering length and effective range. Just to mention, the scattering length is a minus A, where we just discussed scattering in a scattering experiment. So it's just a different notation. But this is used for the simple system, right? If it's one, for example, one spin state. What if we have two spin states, right? But before that, after this modeling in the experiment, of course, it's very difficult to get this done. What do? We measure the correlation in the same event and mix the event and normalize. So that's a very classical way to do this measurement experiment. Just let's go back to how we separate the two spin states in this modeling. Well, just to repeat, well, the first part is a source size, and the second part is wave function. Well, for the spring average case, or say if we just approximate the wave function into one part, well, we call it a spring average, which means we ignore the spring difference for the systems. Well, as you can see in the right side part, well, there's two, for example, for two different, for example, p-Lambda or d-Lambda, well, because the spin of the proton, lambda, and deuteron, right? For the p-Lambda, we can have singlet state, a triplet state. For d-Lambda, we can have doublet state and quartet state. So both of these actually have two spin states. But if we approximate, we just think, okay, use the one averaged spin wave function, use a one wave function to to describe this physics. Well, we call it spin average. Well, if we use separate two spin states, then the wave function can be approximated into two parts, where these two fractions are decided by the quantum mechanics. And specifically for the d-Lambda correlation, there are 1/3 and 2/3, and then the rest of part are the same. So for this case, for this spin separated case, well, the equation you can see they're same, but they just have different d0s, f0s. Yeah, so this gives you a different corresponding to different spin states. Go back to our experiment. So for this talk, we use BeamNG Scan 2 setups, the fixed target setup. Here shows you our BeamNG Scan fixed target program. We use fixed target from 3 GeV to 7.7 GeV. And for 3 GeV data that today my presentations focus is MUB around 720 MeV. We use 0 to 10% centrality, which gives us around 2500 million, 2.500 million events. And this, we are putting the target at one side of the TPC, so the TPC cover the eta for roughly from 0 to minus 0.1. Then just go through the methodology, the analysis flow chart for the people are not very familiar with analysis. First, after we do the collision, first, of course, we try to identify the particle of interest for us. For example, if we looking at neutron lambda correlation, we identify neutron, and then we use KF particle to reconstruct the lambda. So after identify this particle, the next step, we make the correlation for the same event and a mixed event. In the third step, after we get the correlation function, we do the following corrections. First, of course, a purity correction. We need to make sure the particle we select the particle, really the particle we want to make the correlation, right? Then we try to exclude the weak decay where the particle source may not directly come from the emitting, right? Then we try to remove the track splitting, merging, and the momentum resolution problem because of the detectors. In the last step, after we got the corrected correlation function, we use the Lednicky-Lyuboshitz approach to fit and abstract the physics information. So for the particle identification and the reconstruction, where the top plot shows you the dx and m square cube square, and then for the lower three panel, you see the acceptance for the proton, deuteron, and lambda, where the dashed black rectangle represents the proton and lambda we use for the p-Lambda correlation measurement, as red rectangles represent the deuteron and the lambda acceptance for our d-Lambda correlation measurement. You can see there's when we use lambda, the d-Lambda correlation, we use slightly larger acceptance. That's just try to achieve better statistics. And for the next slides, here shows you the most recent higher precision measurement for the p-Lambda correlation from star, where from the left to the right, the 0 to 10%, 10 to 20%, and 20 to 60% centrality. And those points shows you after all the corrections listed in the left side, and we apply a simultaneous fit to the data in different centrality and rapidity, where we're then show in the purple line. Then so we got the RG, or the source size, for different centrality, and the spin averaged F0 and D0s. So the result shows that the spin average scattering length F0 is 2.32 Fermi plus 0.12 minus 0.11. And for the effective range D0 is 3.5 plus 2.7 and minus 1.3.
So when you use these source sizes which you extract for proton-proton correlations, where you actually know the interaction, how well does it work? So
as actually we are doing simultaneous fit, which means we are not assume we know the size of the
yeah, but it's a source of uncertainty, right?
Yes.
And one way to check it is to do proton-proton correlations. For the protons, you get the source size for the protons, right? So if you do proton-proton correlations where you do know the interaction,
yeah, that's certainly a way.
And then you can make convince yourself that actually your Gaussian has anything to do with reality, or it's just fantasy.
Yes. Yes.
So are you trying to do this, or is that on the program? If not, I would strongly suggest to put it on the program.
I think it's this have been done.
What?
It's already done.
And the Gaussians agree.
For proton, yes.
For proton-proton correlations, we have to use the transport model as a phase space. Then we calculate the correlation function.
Yes.
Then you can reproduce the proton-proton correlation function.
But you want to use the same Gaussian here for the.
You mean the size?
I want to have this Gaussian you extract here, throw it into your proton, and see how well it does.
This.
Okay. It's more complicated than you're thinking, because there's a clear empty dependence.
So?
depend on the empty mass.
Yes, I
Empty,
understand.
the pair empty.
Yes, so.
If you take that into account, it's a inner group inconsistent. And he will discuss
Yeah, we in the
again the empty dependence later.
Okay.
yeah we can put this discussion after we discuss source dependence.
Okay.
So this slides we present the first d-Lambda correlation measurement in a heavy ion collision. From the left to the right, there's for different centrality. Similarly, we do simultaneous fit to the different centrality, and if we limited the F0 for doublet state to be negative and for the quartet state to be positive, then we got the following result. Just one more thing to mention.
What do you mean you limit? This is an assumption.
Right. I will go to the details in the following slides. But before that, there's one specific correlation. Correction, or we try to subtract the contamination from the hypertriton. So why we have this? Because we know the hypertriton can decay to the proton, pi, and deuteron, right? It cannot directly decay to lambda and deuteron because of violation of energy conservation. But to our experiment, because this plot shows you the reconstruct lambda, where when we do the some particle and lambda correlation, where we reconstruct lambda from the pion and proton pair, right? And then also shows you the decayed pion invariant mass or pion proton pair. So you can see in experimental limited by the detectors, they are not distinguishable. So that's why this is mixed in our signal event. Where if we do a simple calculation, we can get the K star if there's pion proton pair. If we make correlation to the deuteron, they mostly contribute the K star roughly 20 MeV. So if this is the case, this means this could affect our small K star region. Here I just try to put a cartoon of how this decay, and when we try to use reconstruct the lambda, we make the correlation. This would affect our
What
result.
spin state is the hypertriton of the two you had?
I think for the ground state, right? So it should be the one half, right?
So this should give you a huge repulsive amplitude right at threshold because it's barely bound, right?
Yeah. So
you include this in your calculation? And
exactly. So what we try to do, we based on the hypertriton measurement in the experiment, based on the hypertriton yield, we build this Monte Carlo flow chart where it can generate the hypertriton and make it decay, and then add this our efficiency loss, topological cuts, acceptance cuts, and then compare with the mixed event. So in the end, we get the right side plot. This shows you the 10 to 20% centrality, where the black point shows you the hypertriton decay, the correlation between deuteron and the proton pion pair. And the uncertainty box came from first of decay algorithm, different decay algorithm, then the uncertainty, mainly due to the hypertriton yield uncertainty that in the experiment measurement. So just to summarize, this simulation based on the hypertriton yield measurement gave us around 4 to 8% of deuteron lambda entry for this decay at K star and 100 MeV. So for the 10 to 20% centrality. Well, this combination of subtract from the inclusive deuteron lambda correlation. So to the fit, I put one more slide to describe how we do that. We in the model, in the LL model, we have emission source and final state interactions. For the emission source, we have R1, R2, R3 for 3 different centrality. I mark in different colors, but they should have the same final state interaction parameter. There's 2 groups of them. For the doublet state, for example, this is example I mark in the purple, and then for the quartet state here I mark in orange, where they give us 3 different curves, and use this we match to the data measurement, then we can calculate the chi-square of all the point, right? After we find the minimum chi-square, we use the Gaussian assumption to the chi-square distribution, where we think chi-square -1, -4, -9 corresponding to 1, 2, 3 sigma. Or this we call it manual scan or the parameter scan to help us find the best source size, effective range, and scattering distance. So here goes to the result. The source size with LL approach, or the red symbol shows you the proton lambda source size for different centrality. Blue point shows you deuteron lambda size for different centrality. Just to mention, so that there's still small differences here, because this RG is not one single particle's source size. It's an equivalent Gaussian distribution R for the pair particles. So that, which means for the different particle pair, or for the particle has different MT, you could still have different R, right? And then, but we can find, well, here after this fit, we know this, we could separate the emission source from the final state interaction, and this very simple collision dynamics is just as we expected. We found in the most central, after the free fit, we find the RG in the most central event is larger than the RG in the peripheral event. We also find this RG for the p-Lambda is slightly larger than the RG for the d-Lambda, where just the simple image of this is like the heavier particle flies slower, so the corresponding source is smaller. And then for the different spin states, where here I again put the parton for the proton lambda system, deuteron lambda system. Both of them actually have 2 spin states. So, and this fraction shows you how these 2 spin states, the fraction of these 2 spin states. Where for the p-lambdas, current statistics is not enough to separate 2 spin states. Actually, we are doing a spin average fit. We're shown in the right side plot, where the green curve shows you the best fit, the total, or called spin average fit to describe the data with LL approach. Well, for the deuteron lambda correlation, we use separate spin separate fit, where this gives us a doublet and quartet state. And the next slides, I will explain why we can do such. But for now, where you can see for the doublet state, it's it's lower than the quartet state curve for the most smallest K-star place, and also it go back to no correlation, which is 1 earlier than the quartet state. Here shows you the contour for the scattering length and the effective range. So where from this equation we can see because the d0 is the second term of this approach, so expansion, so the constraint of the effective range is weaker than the f0s, of course. So in this plot, where the x-axis are the scattering length, the y-axis the effective range d0s, where all the points shows here are from the model calculation, where this green points shows you the singlet and triplet f0 and d0s for the p-Lambda correlation, where this red contour shows you 1, 2, 3 sigma for the p-Lambda spring average fit. And for the d-Lambda, we have shown in the blue color, and for the doublet state, we found 2 model calculation, or shows in these two points. And then for the quartet state, we found 3 calculations, shows in the 3 triangle. So our result shown here. So this help us first of all help us understand where this first measurement of this scattering length and effective range for d-Lambda correlation will also help us separate these 2 spin states based on this.
So maybe an effect, a scalar wave, I was confused.
Mm-hmm.
In your convention, a positive scalar length corresponds to attraction, not repulsion.
That's, yeah, very good question. Actually, it's not that simple match for the positive and negative But just to simplify, if so this actually is one thing I want to discuss in the following slides. But if we found the negative, and this could indicate that there's a bound state of this system. So,
but if you have a bound state, then the scattering depends. Then you should see a huge repulsive scattering. If you just have a bound state, right, a very shallow bound state, because then you scatter off this bound state, and this gives you a repulsion.
It is very big.
Yeah, that's why I'm asking for the sign convention.
I think
Yeah.
if you look at the effective range formula, F has to be negative in order to have a bound state.
Okay.
yes,
Proton is only 7.
Yeah.
This is 20.
But proton is attractive, whereas proton neutron in the neutron channel is repulsive.
yes.
So okay.
One another interesting observation is like we can find this F0, the absolute value for F0 for d-Lambda system is much larger than the p-Lambda system.
Yes.
And the F0, if you remember what we discussed just now, the F0 also corresponding to the scattering length corresponding to the cross section. So this means the d-Lambda do have a much larger cross section.
So a proton neutron in your convention has a positive or negative scattering length in the neutron channel. If I do proton neutron scattering in the neutron channel, would I have a positive or negative scattering length in your convention, F0?
It's just opposite of the tradition, A1.
Yeah.
Well, the traditional depends whether you come from high energy physics or from nuclear physics.
Yeah,
That's
that's what
no
I'm saying.
problem.
Okay, when I say tradition is low emission.
No, that's what I'm saying. If you look at the effective range formula,
Yes.
in the quote unquote low energy or nuclear physics convention, that would be negative 1 over A.
Yeah.
And you'd say that proton neutron in the neutron channel has a
Yeah.
positive A.
Yeah.
And so this,
Okay.
This is the different, just the opposite sign of this. Okay, so one good thing I think for this is if we use the base formula and from the effective range expansion and use the doublet state for the F0 and D0s, we could calculate the bending energy or called lambda separation and energy of from the hypertriton. We could calculate this, and the left side shows the plot where all the bottom 4 points shows you the measurement in 1970s, using the Kayan chamber and the emission experiment, where the top 2 points are from the heavy iron collision using the environment mass method from both star and ALICE. This blue bind shows you the fitting for all those green points. Or the top point, the red and yellow, shows you 1 and 2 sigma from this analysis based on the F0 and D0 we estimated from this study, where we could see, right now we can say, oh, well, it's 95% confidence limit shows us consistent with world average. Well, this gives us a new way to constrain the hypertriton bending energy and also probably help us understand the hypertriton structure. Yeah. So here goes to the discussion. Some more things we try to understand and also try to bring up for today. Where there was a seminar actually happened in this room a few weeks ago, I believe. So in ALICE, we tried to do three-body dynamics, right? For this three-body, well, in the left side bottom cartoon. For this topic, for this slides, we discussed, p-Lambda, d-Lambda. For them, they did the PD, where it's just the top 2 particle correlation. Or in their measurement, they found that it's not cannot be simply described by the simple LL approach. So they try to consider a three-body where they consider all the spin states and the fractions, and then get this shape after they even consider the D wave, not just the S wave, to fit this this small hint here. But for LHC, where they are using proton-proton collision, where the RG is very small. So if you if you still remember at the beginning, we discussed LL approach, where the LL need first the smoothness approach. Then when the particle or the particle are probably equal or even larger than the source size, I don't know how much this approach can still work, right? But this still reminds us, right? If we consider or how much the effect for this three-body effect for our d-Lambda correlation for star. So I call it the three-body problem. Where the next discussion is the potential for the particle pair. Whereas we discussed actually in the middle of the presentation, so if we construct, right, if we know the potential and also know the wave function, we could use the potential and wave function to get this correlation function. But now we have correlation function measurement. We could use this and go back. Now we have RG and F0 T0s. This gives us a chance to go back and get the potential, which is our original interest of this analysis. So besides, right, because if after we have this potential, right, we could, for the different case they could help us find if there's a bound state particle, right? Okay, so the next slides, I want first thanks Wenbin because this work I had a lot of help by him. So we try to use Bayesian analysis, try to study the parameters, where I could put a flow chart for the Bayesian analysis. You have a model input similarly to what we did for the parameter scan. We just sampling n set of parameters, they all by uniform distribution. Then we also gave it data measurement, one set of parameter, and put in the Markov channel of Monte Carlo, and to train this model, and after resampling to directly got the possibility distribution for all the parameters. And so this technique, the advantage of this technique is, first of all, it's super fast. It's 10 times faster by just roughly estimation in terms of computing power. And if you do the similar work, you may know, well, if you do the parameter scan after you increase the size of the parameter, or just has 1/2 of small steps, right? The computing power time is like exponentially increased. So this gives us a very good tool to do this analysis.
10 times faster than what?
Than the manual scan, that's just roughly estimation to achieve the same precision. Right.
So doing a Monte Carlo is 10 times
Yes,
faster.
yeah. So the right side shows you the most recent result using the Bayesian analysis tool, while the bottom plot shows you the doublet and quartet state. As I mentioned before, there are constraint fit where we fix the doublets to be negative and quartet state to be positive. Where previously, if you want to increase the fitting range, that takes you a huge amount of time. And then now with this technique, we could do this. Where this, if we free all the parameter for the doublet and quartet state, we could get something like this. This represents 1, 2, 3 sigma for the doublet state and the quartet state. So, but this is still under developing, and this. One more thing for the Bayesian analysis, but right now we can say, okay, this agree with our previous manual scan, parameter scan. But this technique gives us opportunity to reconstruct the potential in a future analysis, because now we just need to tune the potential and put in the Monte Carlo, replace this part, and this may give us a potential of the particle pair. Yes.
So here the second part, the top 4 panels are saying that if you don't constrain it to be negative, there's more probability for
positive. Yeah, positive, even doublet state. Yes.
So should we constrain it to be negative?
Well, this based the negative based on approach, we know the d-Lambda system can be can have this bound state, right? So we'll say the bound state tells us the F0 for doublet state to be negative.
Right, but from the correlation function, you have more probability to get the positive value.
Yes.
Wow. Okay, so bound state is only a small probability then. Bound state only has a small probability and you shouldn't constrain it to be negative. Is that the conclusion?
I think you would say, given the model more likely supports an unbound state. But then what they're saying is the constraint you get from stars suggests you limit the model space to a region. That's my conclusion.
But why would the model give? Why would the model give?
I think the model has coefficients for the positive and negative, right?
Yes.
So that changes the potential. So I assume that bottom right and upper left, that looks like the correlated coefficients in the red panel in the upper left.
This triangle thing
Yeah,
in the middle. Yes.
I assume those are the coefficients of the model.
Yes.
And I think what you're saying, if you don't constrain those coefficients, the model space is likely to produce a positive or unbound state. But given the information you have with all that correlation, it's saying you should restrict the model space to reproduce something you know. And in that case, you should encourage that to be negative.
Exactly. I agree. I think.
You have some physical input constraining your prior.
Yeah.
Right.
But this is like a further assumption. So physics, I call it.
Yeah, it's a physical information to
Yeah.
inform the prior.
So maybe this answers my question, because when I look at your correlation function as they are, I never see the repulsion from the bound state. I mean, they're just going up your correlation function.
Yeah.
Right?
So
At a small q, I would like to see the correlation going down, right? And we don't see that really, right?
so actually this part is something we think they're most sensitive.
No, that should be happening right at threshold. If it's really the hypertriton, which is bound by what, a few keV, right? That's it's right at threshold. So you should go up, and then right at k star equals 0, boom, your thing should go negative, right?
We don't have statistics.
Well, but you don't even see a trend out there at 0.
Yeah, we don't see.
And that's why what the fit says, the fit doesn't want to see this if you let it loose, right?
Yeah.
So it's not in the information, the data is not there yet, right?
It's not
to see that.
informative.
Exactly.
Okay, here concludes my presentation for today, where we present the first neutron-lambda correlation function measurement in the heavy ion collision, the new p-Lambda correlation function measurement with 3 GeV Au+Au collision, which could successfully separate the emission source from the final state interaction for both systems. We observe the RG relations for the most central larger than peripheral, p-Lambda larger than d-Lambda for the same centrality. We observe the p-Lambda scattering length and effective range for the spring average fit, and also d-Lambda correlation for the spring separate fit. Based on the effective range expansion, where the hypertriton banding energy at 95% confident limit agree with world average. So some outlook, we will have 10 times more statistics for best two. So this gave us a chance maybe to further look at the question we still have. For the emission size, we could also look at the emission size versus different energy rapidity, and we could also look at different baryon correlation function to help us fill the map we have right now. So that's all. Thank you.
Thank you very much. Very nice. So questions or comments?
Yes, can you just go back on that? So you said, I mean, about the source size, you said the neutron lambda should be larger than the proton lambda because the neutrons are slow. The neutrons they are probably slow.
Yeah.
But they are also formed, the common belief is that they are formed late via coalescence. So from that, I would have thought naively that the neutron's source size is larger than the proton source size.
Yeah, this could also be meant. both of them.
That doesn't work, that's against this.
This against, but this could be a competition, right? Because the proton could be any time of this process. Then, which means you are not getting a Gaussian, probably got a Landau proton source, and then this, the overall, you give us this.
So you don't, I mean, your data are good enough to play now with non-Gaussian source sizes. Right?
I think that's the limit of this one.
Exactly. Right. I mean, well, if your data is sufficiently good, you could, of course, then say what happens really when I do my Bayesian machinery and I play with non-Gaussian sources, right? I mean, who believes that we have a Gaussian? Nobody believes that we really have a Gaussian. Right?
From proton-neutron correlation,
Yes.
we also analyze to depth. We can see the Gaussian radii.
Mm-hmm.
We also can look into the transport model. We see the long tail.
Yes.
Gaussian cannot get it. Right. And it's also reproduced the correlation quite well.
Okay.
I think that's the only path if we want to limit to this model.
Yes.
So whether it is against the neutron formation scenario. But remember, if you want to see the final state interaction, you have to have these two pairs close to each other.
Right.
So that means those protons do not see those late neutrons. That's the only way I try to see Gaussian. Otherwise we cannot explain. We have to travel with the proton neutron.
Yeah, so I'm wondering how sensitive or important in this LL model is it that you can describe the interaction with an effective range expansion? And then the reason I ask is because strictly speaking, the effective range expansion is not valid once you go above the T-channel cut, which is a pi exchange. And for the two nucleon system, the T-channel cut occurs at pretty low. I think K star is your center of mass relativistic momentum, is that right? So this cut occurs pretty low, like, I don't know, I think it's something like 50 or something. So it's the data you're collecting is certainly in a region where your effective range expansion should analytically break down, or should no longer be the correct analytic description of the amplitude. And so I don't know how important that is.
Sorry, which way is it breaks down? Low K star?
Yeah, or no, once K star gets above,
High K star is great.
but it's not very high, my point. The T-channel cut for two nucleon is, in energy, it's only like 2.5 or 3 MeV. In translating into K star, I think it's somewhere around 50 MeV, if I've done my math correctly, but it's not very high.
Almost all physics is below 100.
Yeah, but I think the cut is below 100 MeV is the problem. So it's like once you get above the T-channel cut, you develop logarithmic singularities that you need to describe the amplitude. And so my question is, how important is the model to really need the effective range expansion? And also, I do know secondhand, as I haven't done it myself, that even though the effective range expansion breaks down for two nuclei, it seems to work well beyond the region it should. But then once you throw in hyperons and you start having particle exchange diagrams, I'm not sure. I think you're gonna have some closer energy thresholds, which might cause some problems.
We tried with proton-proton correlation, tried with proton-neutron and neutron-neutron. All work. Okay.
Yeah. All match the.
But we do have problems.
Can you give us the reference you made in this T-channel thing?
I have an old scattering theory book. I don't have a good reference. I'll find something, yeah.
Thank you.
I guess what I'm wondering is, could you put in a more realistic model for the amplitude?
Well,
the effective range expansion?
Well, that we need probably some help from Siri friends. But before you say something, yeah. So, but we do check if we fit up to 100 MeV. So this returns to the same result, consistent. Which means if the expansion effective expansion work in the below 100 MeV.
Yeah, but what if, strictly speaking, you have to stop at 50? Does it work if you do you get
Well,
the same answer if you look at
we need to know why there's a 50.
I don't know,
Yeah,
yeah.
That's why I was asking for reference.
Well, the other thing I can't do off the top of my head is when you do the 3-particle system, you'll have diagrams where you have some bound 2-particle system exchanging a spectator, hitting the other guy, and there'll be some very nearby energy thresholds that could cause you problems.
That's
Because I know like the triton is a case where if you look at the amplitude, in order to see the fact that you bounce state in tritium, your amplitude has to run through infinity in order to find the bounce state point. And so that, then you definitely won't be described by that amplitude.
Okay, any other question or comment?
Another question, how you get one formula for this new?
oh they this one, right?
Yeah.
So they have an MT scaling map. So they try to when they look at the particle pair, probably have this in my backup. Yeah, this one. Okay, this one. So they look at this for their mean bias high multiplicity data, or for different particle pair, they just use this curve to interpolate what would be the source size.
I see. This is Laura. So for theory side, this LL model, the second L died a long time ago, but it's very difficult to get in touch with
The first day.
the first L. He's the associate director at Google. So it's very difficult. We send a message after 3 months later and see echo from agent universe. So that is very difficult. We cannot answer your question. Which range is valid for this approximation?
Or maybe another starting question is, do you really need an effective range expansion? Or can you just use an amplitude?
Well, you can solve the Schrödinger equation.
Yeah.
Okay, so solve it. We'll use your model.
No, but I mean, Scott has the program, right? I mean, and you guys have it on your plan, right? I mean, that you extract the
Very good.
potential and then do it.
Exactly. We don't have the potential, especially for neutron. Do you actually have this? Can you?
Give me 10 years and
We give you 10 years. So this is really beautiful measurement.
Okay. I'll add to this one of the important of this measurement.
Yes. Can you please go to, there's no question from online here. Just one, yeah, just on this slide. If we more discussion to Suraj's question. If you look at the top 2 panels, we spend hours just discussing this plot already. Top 2 panels is a fit with plus minus 40 for no restriction. The top panel, panel A, is for it's for
Doublets.
doublets. Sorry, I cannot.
Q. Okay.
So you can see clearly there is it's positive.
Yes.
It's a positive orange color. But when you go to doublet, which we know there is a bound state, and actually this open fitting also gives us a hint. You can
That's
see
in the
magnetic
third
side.
sigma.
Yes, second, it's a 2 sigma. 2 sigma. 2 sigma. And once you add theoretical, we call that theoretical constraint because the model prediction, you can see clearly. But we are not sure this constraint is fair.
You should see it in the data.
Well, it reminds me of your comment about
we
the.
do see in the data. That's what I'm trying to say.
No, but knowing your correlation function, eventually if you have the mother of all measurements,
Oh, yeah.
you should see a correlation function, boom.
I was
No,
thinking from
that is Coulomb, right?
No, it's your repulsive interaction
That's a bounce.
from the bounce.
But to me, this is also okay. Okay, your boom is boom, but this is.
Yeah, but your data is
information.
not precise enough to see it, right? I mean,
I
so.
agree. That's the current standard.
But it could be that the model of the amplitude to describe interaction gives you the wrong value. That's like, you know, experimentally there's a bounce in the binding energy. Right? Is that correct?
Yes.
Yes.
This is hydrogen 3 lambda.
Yes, hypertriton, yes.
And so if you had the correct amplitude to describe the interaction, you could put that constraint into the model.
Neutron plus lambda will not give you a binding to hypertriton.
Of course not, and that's why it's repulsive. You go virtually, quantum mechanically coming with a neutron and a what is it called, a lambda,
Yeah.
but the system knows, of course, that there is a bound state below the threshold, right? Energy momentum conservation doesn't let you go there, but virtually you can go propagate through this and go up. And then you just do second order perturbation theory, you immediately realize that this leads to repulsion. And the closer you are to the threshold with your bound state, because you have an energy denominator, 1e over e binding, and poof, it goes off.
So what you say is the positive F0 repulsion part is clearly demonstrated when you just said.
The repulsion, yes, meaning a negative correlation function, but a positive.
No, it shows in that fit result. The positive part.
Well, yeah, assuming.
I would like to see a dip in the correlation function, right?
To me, it's the same thing.
Yeah.
No, but that,
Physics-wise, the same.
that depends on the effective range expansion being a valid
Yeah,
description.
I agree. Agree. You say you are continuous questioning the model.
Yeah. But that's what I'm saying, to draw this
Yeah.
conclusion, you have that assumption. Yeah.
Yes, that's also what our worry, whether this is the case or not. Why we spend hours and make 3 panels instead of only 2 panels.
I was gonna say, Volker, your comment reminds me of thinking about the problem a different way. If you look at the scattering phase shift, if you look at the proton-neutron phase shift in the deuteron channel, it goes up to 180 degrees
Exactly.
because there's a bound state.
Right at threshold, right?
And if you were to look at neutron-neutron scattering, so however you want to cook, you take some experimental data, rip off Coulomb, and do. If you're looking at neutron-neutron scattering at very low energy, it also is rising steeply as you come to low Q.
It won't make it.
But only if you have data at very, very, very small Q do you see it suddenly turn over and drop because there's no bound state.
Small Q always difficult.
Yeah, exactly, yeah.
No phase space.
But I think that must be the same information package, either.
Oh, yeah, of
correlation
course, of course,
function
of
or
course.
the phase.
And the thing it's bound by what? 400, I mean, what? I mean,
KeV,
That's very small.
very small.
yeah, so
Also, I think that global average is, it's only so small because of tension in the fitness or in the experimental data.
Yeah.
Like if you did the PDG √2 or square root inflation, you're certainly quite a bit bigger. You'd be more consistent. Oh, no, it already says there's an
It's
F factor of
included.
1.6.
Exactly.
Oh, my.
So it's bound, that's what we know. And it's a couple of KeV, right? It's not even an MeV, right? So it's closer to threshold than the neutron. So the effect is the scattering length must be huge.
Yeah, so the phase, yeah.
So this is the first measurement. To what extent helps to understand theoretically, because there are already many calculations in the past, especially by from Hammer. Darmstadt.
Yeah. So the closest thing that comes to mind is I know Hammer and Paul Badaki were involved in the tritium. And if you look, or maybe this predates them, but if you look at, I think, neutron deuteron scattering, amplitude cannot be described by that simplistic effective range expansion, because as you're coming from large Q to small q, the amplitude actually has to shoot up to infinity or something and come back. And so that would look like an effective range expansion with the wrong sign residue. So like your f of k is the inverse amplitude, right? Or no, it's actually inverse. You have the ik in there as well. So it's the t, it's the amplitude, yeah. So I have to go do some research. I have to go do some homework. It's not research, it's already known.
At least to myself, I was not very happy. You see our contour very consistent with the blue triangle, which is the model calculation.
Yeah, this
Those are
purple.
really critical.
Blue, I don't see a blue triangle.
This purple
Can
kind.
you? Purple. Colorblind.
Obviously.
The purple consistent. In both cases, probably in the cortex.
You're unhappy with that.
So what calculations are those? These
Information.
Yeah, I'm not an expert on this, but they this from the timeless effect. Do you see?
effective field theory? Yes.
Yeah, timeless.
But the finalist EFT is one of the few EFTs that actually works.
Yeah, but that's
So they have reference there, right?
Yeah.
That's all.
so is that hammer or something like
Hammer,
that?
yes.
Yes, the first one.
But I also remember the calculation, not really 3 body. No. Actually, 2 body.
This is two bodies.
Yeah,
So if you go to,
two body,
if you go to really low energy, yeah, the deuteron can be treated as
point particle.
really a point particle. I guess it's such low energy, if it's really KeV, maybe you can't break up the deuteron, so you're really below the deuteron breakup threshold.
Of course, what we really want is the lambda nucleon, not the lambda deuteron interaction.
Yes.
The lambda neutron, to be precise. Coming back to your first slide of this beautiful neutron star, right? So,
Wait for 10 years?
no, I mean, what one needs is people like Andre and data from you up to helium-3.
Yes.
That is coming.
And then one can dissect it.
How expensive is your experiment?
Sorry?
How expensive is the experiment?
Our experiment, it's very cheap, it's actually free.
I mean, the whole,
Star is a collider.
I was just gonna say,
This is a fixed target.
I was just gonna say, just give me like 5% of your collider budget, we'll build a computer.
So tritium, is that possible from the statistics in helium-3 with the 2 billion events you have this out?
So we will try at least.
So did Hammer use that effective range formula? He'd know all these problems.
I
he's
don't think
talking
so.
about.
I don't think he used that formula. He did his own calculation.
But he would know all these problems very well.
Absolutely.
No, actually, it was he brought up this issue. He said this is not a measure. It's a measure.
So the outside question, so this can be only done in the beginning scan, any other experiment you can do the same thing?
CPM, they have
All the
statistics
CPM,
like
or
crazy.
how about the RIG 200, you cannot do?
Well, the baryon density is very low, therefore this correlation functions, the pairs are very small. Statistics,
Yeah, but you can
Oh,
still
you don't
do
have
the
any
statistics,
particle,
yeah.
that's why.
it's not too many baryon pairs.
But at least it is, that's for the, I'm still back to the question, how they determine at least the size?
Size of.
So what does that mean? So you also have argon plasma?
For them, I don't know.
This is PP collision. There's no quark plasma is assumed.
Okay,
They measure the proton-proton correlation.
okay,
Then they assume pair MT dependent.
okay,
Then they decide use the size.
okay. So what's the conclusion?
Conclusion, they say they can separate the size part and the final state interaction.
So what size? So that means that
Size.
there's something created in PP collision at
Yes.
least?
It's about 1.4 Fermi, I remember. Yeah, you see the maximum is 1.4.
So there's a source.
This
This
is
source
the
has
source of the baryon pair. They are different from baryon, specific baryon.
For me, it's very hard to understand this physics. I mean, you think about it, right? So in the PP harness scattering, you found something which is very related to your 3D UV ion creation.
Because it's final state direction. At the end of the day,
Yeah.
it's hadrons which fly towards the detector, and that's when all this happens.
After freeze out, let's say the real strong interaction stops. These two particles fly each other, and they form. They start to interact.
Okay.
Or interference happens.
It's just like a low energy proton-proton scanning experiment, except you don't have plane waves, like in an accelerator. And therefore, you need to know the source size, that you know what sources of
How to
particles.
separate these two.
Yeah. If
So
you had
this, for
plane
example,
waves, then the source size would be totally trivial. And then
so
you
this
do your standard finding
this
size.
two probably has to come from same jet. For example.
Same one.
J.
No,
Oh,
they have to come from the same mass. They have a bunch of particles.
Presumably the source size limits how small in energy you can go.
I mean, it's not a question, right? For example, you asked if a neutron is formed in the really later time.
Yes.
So I would assume that, for example, if this kind of soft particle, they also formed in very late time. So how you can actually say that is within one formula, right?
Oh, extracting the source size. Well, I mean, with a proton you can do this because with a proton you know the interaction extremely well. So when you go with formula, the formula is correlation function is integral over source times the wave function.
So I was trying to think about this. So another outside question, can we do this in the EA region?
I think so.
I'm not sure whether it's very successful because you don't have much sources for the world.
There's a general program, it's called K factory. Basically try to convert OD into a K factory. So they were like KM.
Okay.
KM. So they would have not around us.
But there, they don't have enough barrier.
What
Because
kind of
your baryons sit in the target.
That's right.
Not in the interaction. You can generate, because this is called strangeness production.
Yes.
So you don't have barrier. You have strangeness there. SS bar.
You have strangers.
Yeah, you don't have barrier.
That's a nuclear target, right?
Yeah, but target is far away from.
But you need the proton and the lambda fly together.
Yeah, and a very similar moment.
Small red momentum, whatever,
Yeah.
100 MeV or something, 50 MeV.
Below 100.
But if they produce the lambda also in no transfer, no movement.
You can measure, I'm pretty sure, just the question is experimental question, do you have enough pairs to do this, especially at the K star equal to 0? That is like 10 years. Okay. All right, any question from online? So many UCLA people there.
We're done with the CME.
So if not, let's thank you one more time. Okay, thank you. That's the end of today's seminar, and see you next week. How do I stop them? How do I stop them?
Stop here.
Turn off the computer.